Albert Einstein. Okay, the name. Everyone knows it. EMC the photo with the tongue out.
Hmm.
It's iconic.
Instantly recognizable. Absolutely.
But how many of us have actually, tried to read his original work, the actual paper?
Yeah. That's a different story. They can be notoriously difficult to get through.
It feels like trying to read the universe's source code, but it's where the real revolutionary ideas are buried. So today, that's exactly what we're doing.
A proper deep dive.
Exactly. Into the foundations of general relativity, cosmology, even the unification of forces, straight from Einstein himself. We're looking at the foundation of the general theory of relativity.
That's the big one from 1916.
And Hamilton's principle, cosmological considerations. Do gravitational fields play an essential part? The core stuff. Plus a little bit of whale on gravitation and electricity.
Right. So the mission here is really to help you cut through that complexity.
Yeah, pull out the key insights, give you a shortcut to understanding this massive shift in how we see the cosmos. So where's our starting point on this journey?
Well, our mission is to help navigate these, let's face it, complex original texts. We want to reveal those profound shifts in thinking that really redefined physics.
Okay.
So I think we have to start with why. Why was general relativity even needed? What was missing from special relativity?
Right. So special relativity, that came first. It worked brilliantly for things moving at a constant speed, nice and steady.
Uniform motion. Yeah. Based on Galileo and Newton's mechanics, plus the constant speed of light.
But yeah, what happens when things speed up, slow down, accelerate? And the big one, gravity. That always felt like the elephant in the room for special relativity, didn't it?
Exactly. Einstein saw that the special principle was just that special, limited. It only worked in those, specific cases. He pointed out what he called an inherent epistemological defect in classical mechanics and even special relativity when it came to gravity or non-uniform motion. He even noted Newtonian mechanics doesn't quite nail causality in all scenarios.
Causality, like cause and effect.
Yeah. And how physical laws appear to someone who isn't moving uniformly, someone accelerating or falling. He realized, for laws to be truly fundamental, truly universal, they had to work for any observer in any state of motion.
Not just the special, uniformly moving ones.
Precisely. Any system of reference. That was the goal. And that meant tackling acceleration and gravity head on.
Okay, so special relativity kind of hit a wall there. What was his next move? Did he just try to bolt gravity onto the existing theory? Or was it something, more radical?
But much more radical. He didn't just tack on a force. He completely reimagined what gravity is.
Right.
Social relativity had already linked space and time, showing they weren't separate but part of this four-dimensional continuum, 3 space dimensions, 1 time.
The space-time we hear about.
Exactly.
Yeah.
General relativity took that idea and ran with it, fundamentally changing how we interpret that space-time physically.
So wait, instead of gravity being like an invisible rope pulling things, Einstein said it's about the shape of space-time itself.
That's the core idea.
Like the classic analogy, the bowling ball on the trampoline. Making a dip and that curve tells other things, like marbles, how to move.
That's a great way to visualize it, yeah. Mass and energy warp space-time, and that warping is what we experience as gravity. A free particle just follows the straightest possible path, a geodesic, through this curved space-time.
And this idea of general covariance, that seems crucial. It means the laws of physics look the same for everyone, everywhere, no matter how they're moving or accelerating.
Absolutely crucial. That's the general principle of relativity. The laws have to be expressed by equations that are covariant, meaning they keep the same form, regardless of the coordinate system you use.
So it doesn't matter if you're floating freely or spinning wildly, the fundamental laws remain unchanged.
That's the requirement. The gravitational field itself becomes part of this physical geometry. But describing laws that way, making them look the same for all observers. That needed a new kind of mathematics.
A new language for the universe, basically. What kind of math can do that?
Tensors. That's the key.
Tensors, okay.
Think of them as, mathematical objects that can represent physical quantities like velocity or stress or curvature in a way that doesn't depend on the specific coordinates you're using to measure them.
So they capture the underlying physical reality regardless of your perspective.
Exactly. They're the tools needed to write these general covariant equations. And central to the whole theory is one specific tensor, the fundamental tensor, usually written as Guillemin.
And this isn't just abstract math. It actually describes what?
It describes the gravitational field itself. It defines the geometry, the metrical properties of space-time at every point. It tells you how to measure distances and time intervals in this potentially curved landscape.
Wow. So this gummy new thing is the curvature. It's how mass and energy literally shape the space-time around them.
Precisely. It encapsulates that relationship. The gravitational field isn't some mysterious force acting in space-time. It's a property of space-time itself, determined by the matter and energy present.
Okay, that is genuinely mind-bending. So he develops this whole new framework, these field equations linking matter to curvature. But the real test is, does it work? Does it explain things the old theories couldn't?
Ah, yes. The predictions. This is where it gets really compelling. The theory wasn't just elegant. It made specific, testable predictions that differed from Newton's gravity.
Like what?
Well, two big ones stand out immediately. First, the orbit of Mercury. Astronomers knew for decades that Mercury's elliptical orbit wasn't quite stable. It was slowly rotating, precessing, in a way Newton's laws couldn't fully account for. There was this tiny, inexplicable remainder, as Leverrier found.
Right, the perihelion precession.
Exactly. Einstein's theory, when you crunch the numbers using his field equations, predicted exactly that observed extra wobble. It just came out naturally from the curved spacetime near the sun.
He must have been thrilled. It wasn't just a new theory. It solved the long-standing puzzle.
Absolutely. And then there was the prediction about light.
The bending of light, that seems even wilder. Like gravity can act on light itself.
Well, light travels through spacetime, right? So as spacetime near a massive object is curved, the path of light should curve too. The theory predicted light rays passing close to the sun would be deflected.
And he calculated how much.
He did. The paper mentions calculating a specific deflection, about 1.7 arc seconds for light grazing the sun. This was famously confirmed during solar eclipses a few years later.
Wow. Okay, explaining Mercury's weird orbit and predicting bent starlight, that's some serious validation.
It was huge. It showed the theory wasn't just mathematically consistent. It described reality better than Newton's did in these extreme cases. And you also mentioned Hamilton's principle earlier.
Yeah, what's the connection there?
Well, Hamilton's principle is this deep idea in physics that systems tend to follow paths of least action. It's another way to formulate physical laws. Einstein showed that his field equations could also be derived independently using this principle.
So, like, approaching it from a different angle and getting the same answer.
Exactly. It provided further theoretical support and also helped demonstrate how energy and momentum were conserved within this new relativistic framework. Really solidified things.
Okay, so general relativity changes how we see gravity locally around stars and planets. But what about bigger, the whole universe? Did it force a rethink there, too?
Oh, absolutely. Applying general relativity to the cosmos as a whole opened up a whole new set of questions and challenges. Einstein realized that Newtonian cosmology had problems, especially with infinity.
Infinity, how so?
If you assume, like Newton implicitly did, an infinite space filled more or less uniformly with stars, you run into issues. Gravity would theoretically add up infinitely, leading to infinite forces or potentials. Einstein called this another epistemological defect. It just didn't seem physically sensible.
Okay, so infinity was a problem. How did GR handle the universe's large-scale structure?
Well, to make his equations work for a universe that was, according to the thinking at the time, static, not expanding or contracting, and also finite, to avoid that infinity problem, he had to make an adjustment.
An adjustment?
He introduced a new term into his field equations, a constant, represented by the Greek letter lambda. We now call it the cosmological constant.
Lambda. What did it do?
Essentially, it acted like a kind of anti-gravity, a repulsive force that counteracted the mutual attraction of all the matter in the universe over vast distances. This allowed for a solution where the universe could be static and stable.
So he sort of balanced gravity's pull with this new cosmic push to keep everything still.
That was the idea. It allowed him to propose a model of the universe that was spatially finite, but unbounded like the surface of a sphere. You could travel forever, but it's not infinite, and filled with a uniform distribution of matter. Spherical symmetry, constant density on the largest scales.
A finite, static, spherical universe held in balance by this cosmological constant. It's like he built this grand cosmic structure and then added this one ingredient to keep it from collapsing.
That's a pretty good analogy. It fit the prevailing view of a static cosmos. Of course, we now know the universe isn't static, it's expanding.
Right, which famously led Einstein to later call the cosmological constant his greatest blunder. Though, ironically, it's made a comeback now with dark energy, hasn't it?
It has indeed. But at the time, it was introduced to solve that static universe problem within GR. It really shows how tackling these fundamental questions about the universe's overall structure was intertwined with developing the theory itself.
Fascinating. So from gravity to cosmology,
Hmm.
but the ambition didn't stop there, did it? It sounds like Einstein and others like Hermann Weyl were already dreaming bigger, thinking about unification.
Yes, absolutely. The quest to unify the fundamental forces is a long-standing theme in physics. After establishing general relativity, Einstein started asking deeper questions about matter itself.
Like in that 1919 paper, do gravitational fields play an essential part in the structure of the elementary particles of matter?
Exactly. He wondered if the very existence and properties of elementary particles like electrons could somehow emerge from the fields themselves, perhaps from a combination of the gravitational field, space-time geometry, and the electromagnetic field.
So not just describing how particles move in fields, but whether the fields could create the particles. Maybe their electric charge was just intense gravity.
That was one line of thought he explored, trying to find solutions to the combined field equations that look like stable particle-like structures. He was trying to incorporate Maxwell's theory of electromagnetism into the geometric framework of general relativity.
Bringing electricity and magnetism into this picture of curved space-time.
Yes. And he wasn't alone. Hermann Weyl, a brilliant mathematician and physicist, was independently working on a unified theory around the same time.
Weyl's gravitation and electricity.
Right. Weyl used Riemannian geometry, the basis of GR, but tried to extend it. He introduced concepts like the transfer of length, suggesting that not just direction but also scale or length could change as you move through spacetime, potentially linking this geometry to the electromagnetic field.
So even deeper geometric connections.
That was the hope, to find a single geometric structure that could underpin both gravity and electromagnetism. But it was incredibly complex.
What were the big hurdles? Why didn't they crack it back then?
Well, finding equations that correctly described both forces and also matched observations about particles proved extremely difficult. Einstein's attempts to build particles purely from fields ran into problems. They didn't quite capture the quantum discrete nature of particles that was also becoming apparent. Weyl's theory, while mathematically elegant, had implications like lengths changing depending on path that didn't seem to match reality directly at the time.
So the dream was there, the ambition was huge, but the path was tricky.
Very tricky. These were early, bold steps on a path physicists are still walking today, trying to find that unified description. It just shows the sheer scale of the intellectual challenge they were tackling.
What an incredible journey. So we started with the limits of special relativity, saw Einstein's leap to gravity as geometry.
The whole idea of curved space-time, described by tensors like Gin.
Then the amazing predictions, Mercury's orbit bent starlight that showed the theory actually worked.
Right, the crucial observational evidence.
And how it forced a whole new way of thinking about the universe, leading to the cosmological constant, even if its role changed later.
The whole cosmological dimension, yeah.
And finally, touching on that grand ambition, trying to unite gravity with electromagnetism, maybe even matter itself, pioneered by Einstein and Weyl.
That early quest for unification.
Going through these original sources, even with the difficulty, really gives you a sense of the monumental conceptual leaps involved. It helps you appreciate just how much groundwork was laid for everything we understand now, from black holes to the Big Bang.
Absolutely. It wasn't just calculation. It was deep philosophical rethinking of our most basic concepts.
So here's a final thought to leave you with, building on all this. If space-time's fabric is shaped by matter and energy,
And if matter itself might just be a particularly intense knot or configuration of that same space-time fabric, as Einstein and Weyl were exploring,
then maybe that line we draw between stuff, matter, particles, and empty space isn't so clear-cut after all.
perhaps it's much more fluid, more interconnected than we usually imagine. What could that imply about our fundamental assumptions about what reality even is?